This is Monday, March 3rd. This is CS 746, Perspectives in Data Science. Today's lecture is going to be a short one on variable selection, continuing up with embedded methods. And after that, I'm going to start talking about the midterm, because the midterm is next week on Wednesday and Thursday. And then, of course, after that, we're going to go on to the spring break. So we'll begin by talking about variable selection here. We already did one lecture on this. It's divided into two lectures. I'm not quite sure why. Mostly to make sure we spend time on other things during the lecture, I think, right? So what is variable selection? Quick review of last week. It is a process of selecting the subset of relevant features from the total features of your data set. So it's figuring out, you've got different kinds of data. Some of your data is, numeric. Some of your data is character. Some of your data is useless, right? So feature selection is to get rid of the useless parts of your data, to find the things that are correlated, things like that, so make ourselves a better model. We get better accuracy, easier to interpret, shorter training times. We reduce the risk of over or under fitting. It makes it easier for us to implement, and so on and so forth. We went through all these last week, right? And of course, bad learning behavior in high dimensional spaces. That's going to be one we'll get into in principal component analysis. We'll start talking about the high dimensional spaces in more details. We'd already talked about filter methods and wrapper methods. Today we're going to do embedded. Filter methods are the ones that are the pre-processing step. We're basically just filtering stuff as we come in to do our work. We're looking at the obvious things like, a data point, a feature that has no variation at all will never tell us anything useful, right? That's only when we see some kind of movement in the measurement that it can tell us anything, give us any predictions, right? So these are just quick screen removal of irrelevant features. You can think of these as almost part of the data cleaning. Of course, data cleaning segues into exploratory data analysis, segues into feature selection. Our filtered methods are basic ones: univariate methods, select k-best, select percentile. Our information gain methods, our Fisher score, looking at chi-squared implementation, our ANOVA F values, and our correlation matrices with heat maps. And of course, we went into more or less detail. Some of these we just glossed over. We're not expecting to use those in our tasks in this semester. There are things that you'll need to know in the future, but you don't need to know them necessarily for this class, right? And other things that we went into in a deeper, and we've been talking about for all along, like correlation matrices. We've seen since early on in the class. Wrapper methods, we try to use a subset of features, train the model using them, and then we try to see how good our model is based on our subsets, and we try to pick the best model from the different subsets. So it's a search problem, computationally expensive. Okay, there's our wrapper methods: forward selection, backward elimination, exhaustive feature selection, which is, forward selection with everything being considered; recursive feature elimination, which is basically backward elimination, but you're considering everything at all steps; and finally, recursive feature elimination with cross-validation, where you're running extra testing in there. Okay, now embedded methods. This lecture only has 23 slides in it, and we've already gone through 10 of them in the review. So embedded methods are iterative. The machine learning model itself is doing the training. It's extracting the features for you. You're not out there, running it and having something on the outside that's, doing things on the model automatically or manually, where it's, evaluating the model externally. It's the model doing something itself. It's using what we call a penalization method or a regularization method. In other words, we put a threshold on the coefficient and say if we fall below that threshold, we penalize the feature, right? Why do we call it a penalization? We consider a regression algorithm. If we're looking at feature selection, forward selection, we talked about Bayesian information criteria, BIC. We talked about adding more and more of a penalization to terms, penalty to new terms, higher threshold on our p-value right? So when we're starting off, we add the feature with the lowest p-value, and we add the feature with the second lowest p-value, and so on and so forth. We can use a hard-coded limit, or we can have one that raises or lowers the limit each step, right? So we're looking for only things that are really, really useful to our model by the time we get out past, 5 or 6 features, right? So we want to bias the model towards lower complexity. Now, our 3 features methods we're going to talk about today are lasso, ridge regression, and elastic net. Lasso stands for least absolute sum of squares. All of these have different built-in penalization functions. So you ask, Python, pandas, sklearn to do a lasso regression. It'll run it, and it'll looking at the features, and as part of the algorithm itself, choosing the most useful features. So we're going to start with the ridge regression. We have highly correlated features in some cases, right? If we've got independent variables, but they're correlated strongly with each other, we can have a little problem where if we're trying to choose which next feature to add or to delete in forward or backwise stepwise selection, there'll be 2 features that are very close to each other, and say the p-values and the change in r squared, right? And so if we had like different data sets, we might choose, petal length versus petal width, right, on our iris data set. So what we want to do is to have something where we kind of, tie the 2 variables to each other more closely so that we can see them, that commonality in their measurements is reflected in the importance in the model. So its variance is in mean square estimators often smaller than the least squares estimators we derive for a standard linear regression. What are we doing? Well, it's putting a constraint on the parameters. We're looking at this kind of a phase space, I guess, here. We're looking at this in a different dimension. This is not a point. This is, if we run an ordinary least squares regression on a set of data, it will give us a line. It will give us a beta 0 intercept. It will give us a beta 1, beta 2, beta 3 for every value. It'll give us a precise number for each one of those, right? So we can think of that as a point in high dimensional space, right? And that's the ordinary least squares estimate. We'll have uncertainty about those, right? We'll be able to say what on each of those, what the residuals indicate is the variance of how good our estimate is. We're not saying we have this is the number. We're saying this is an estimate of what the true number is, and we have a probability distribution about the number we've estimated that says this is where we think the true number likely is, right? So we're going to go ahead and take that ordinary least squares estimate, and if we've driven ourselves to where we're saying our estimate is perfect, it's going to be a point. If we say we're going to say we want this thing to be within 5% of the true value, so now we have a range of numbers, right? We've got a normally distributed residuals. Instead of taking the peak, the mean of our normal distribution, we're going to go ahead and take 10% out the middle, 20% out the middle, so on and so forth, right? So we're going to relax around each of those. And so if we start doing that, you can imagine you're going to see contours. If this is, say, a 3-dimensional ordinary least squares with an x, a y, and a z. Here we got 2 dimensions, beta 1, beta 2, but there's also, think of something coming out. There's a spot where the OLS gave me the best estimate. And then around that, there's an egg shape, or in here, there's an oval shape where, if I relax each of these by 5%, right, then beta 1 will have some variance, beta 2 will have some variance, beta 3 will have some variance, and we'll get a surface or a ellipse around that is 5%, 10%, whatever our numbers happen to be, right? So we're penalizing this by applying a circle about the origin. We're saying that the estimates of our OLS plus our ridge estimate or our ridge constraint right here is we're gonna set the sum of those to be a minimum. So we're trying to minimize basically the area of this OLS estimate plus the area of the ridge estimate, right? If we don't leave this on here, we'll just get a point value here. If we only look for, the least area of a circle about the origin, of course, that's a circle with zero space, right? So the ridge estimate is given by the point at which the ellipse and the circle touch. There's a trade-off between the penalty and the residual sum of squares. There are too many words on this slide. So if we have a large beta value, right, that might give you a better residual sum of squares, but it'll push the penalty term higher. What we're saying here is that, the more closer we get to this, the bigger this blue circle has to become, the area of our constraint. So you might actually prefer smaller beta values with a worse residual sum of squares. So basically, we're constraining our betas to higher or lower values, pulling it away from the best estimate. Correspondence between lambda and c are constant on our betas. How far, we're basically saying that the beta j's, we're not letting them go to zero, right? We're letting them go to some small value. If we have a lambda value, and that is, again, the size of the ridge estimate, because we're multiplying the ridge constraint here by lambda. If we let lambda go to zero, right, we're not doing any constraints. When we let lambda go to zero, the beta j's are where they want to be, right? We're letting the regression run normally. If we start pulling lambda down, we're going to start pulling the constraint further and further closer to the origin. If we set lambda at infinity, we basically say, hit the origin. And we're like not putting anything in our model. We're going to ignore all the arguments. So lasso is using shrinkage, right? Where we're going to start the data values. We're going to shrink them towards a central point, like a mean, for instance, or like 0 in this case. We're encouraging simple sparse models with fewer parameters. Oops, where'd we go? Ridge regression. Oh, we got to talk about it. Okay. So again, as we start pulling this down, we can eventually reach a point where we have no features in the model. As we're starting to go this way, we'll see that we'll get some point where maybe some of our features will be so close to the axis line that we might as well throw them away. But we'd like to be able to have something that's more of a constraint that will allow us to eliminate features entirely, right? So what ridge regression is doing is it's dealing with showing the collinearity or of two different variables, but it's not actually pulling both of those to 0. So lasso is a type where we're using least absolute shrinkage. It performs what we call L1 regularization. Thing up in the front here. Whereas ridge regression is performing L2 regularization. L1 is basically doing absolute values, right? Here, instead of saying this second term is the sum of beta j squared, we're going to go ahead and use lambda times the sum of the absolute values. Our constraint region now, instead of being a circle about the origin, is a diamond about the origin, right? So what we're going to see is we're going to add a penalty in there. So we want to reduce the number of degrees of freedom of the model. And to do that, we need to pull features out of the model, right? So lasso will go out here and say, I'll go ahead and put this constraint up here is this region. If I have a big enough lambda value, or sorry, if my lambda value is small enough, if I multiply this by a small enough value, then it's having minimal impact. And we'd have a giant diamond that would hit right there on the OLS estimate. As you constrain lambda higher and higher, it'll shrink further and further. Did I do that in the right direction? Anyhow, so in this case, we shrink some of these. We have a intersection at the axis. In this case, we can say that we have shrunk beta 1 down to 0. We've pulled it out of the model now. So we can go ahead and say we have this diamond shape and higher dimensions. We can imagine this pulling more and more features onto the axis, right? So the cool thing about this is that we actually shrink individual features to 0. Comparing our constraint areas, lasso and ridge. Again, we have the same constraints or the same contours around our OLS regression, right? We introduce variability in there. The variability will make an egg shape, ovoid shape. We'll be pulling on that area. The question is, where is our intersection with our constraint? If we have a circular constraint, ridge regression, that point of contact is usually not on an axis. It is somewhere up in this coordinate space where your best OLS lies, right? So you're not pulling things to 0. Here on the lasso regression, because we're using a nice absolute value, gives us a nice pointy area, we're definitely going to be pulling things more close to the axis. So again, the RSS ellipse is not usually at an axis. There's no coefficients leading set to 0. The lasso constraint has a corner at each axis, increasing the likelihood. So we got this tuning parameter, lambda, controls the strength of the L1 penalty. As we said before, when lambda is 0, right, we are not giving any weight to this blue-green area about the origin. And so no parameters are eliminated. The estimate is exactly equal to that one found with the linear regression. As lambda increases, more and more coefficients get set to 0 and then eliminated. When lambda is set to infinity, of course, you've got a point right at the origin, and every single one of your coefficients is pulled out, right? So as your lambda increases, the bias of your model increases. But as lambda decreases, the variance in your model increases. In other words, we've got, our beta sub j. We're measuring, how we're relaxing our curve so that we're actually broadening the thing. Our variance is going to decrease as we pull variables out of our model. Right? So ridge regression, if you've got variables that are correlated, it helps make sure that those variables move together, right? And that's a good thing. In lasso regression, it helps with variable selection. But if you've got correlated variables, it can be unstable. It can get down there. If you use two different data sets, collected 2 different places of the same things, it might eliminate feature 1 in one case, feature 2 in the other case. So it's not stable about what to do. So can you get the benefits of both? Yes. And the answer is we can do an elastic net where we combine both lasso and ridge regression. So here's we're trying to minimize our sum of the area or volume about the regression estimate, our area about the lasso, and our area about the ridge regression. So this kind of gives us a sparse model. The quadratic part removes the limitation on the number of selected variables, encourages a grouping effect, pulls things to the axis together, stabilizes that L1 regularization path, and therefore the L1 regularization can pull features out of the model cleanly. So here's our kind of diagrammatic feature of this. We're going to get, sparsity-inducing L1. L2 norm is going to be a weight sharing thing where it's going to be pulling, the features that are correlated with each other in the same direction. And then L1 plus L2 is going to give us a little bit points on our constraint region and is going to pull us to a pull in these case theta 1, theta 2. It'll pull the least valuable one out, but if there are two that are strongly correlated with each other, they'll be following each other in step in that higher dimension space, and it will pull them both to the axis close to the same time rather than having wide variation in it. So I've got several links here for you to reference on doing this, and we need to create a homework for you, but we don't have it ready yet. We'll just pull it from previous. Feature selection is our discussion. Oh yeah, we're down to the last one here. Lasso and ridge regression. And we have a nice discussion on here of, we have some scatter plots, some of the independent variables. Yes, okay, that's fine. Are correlated, some are not correlated, right? So when we do regularization, the values that are, oops, what is this? I don't want to know that. No. Anyhow. So we can observe on here as we start looking at our coefficients, they're going through this in actual Python code looking for examples. So I recommend you go ahead and download that and mess around with it to understand what's going on. You can go ahead and copy paste that code into your notebook. No, you can't. Sorry, the Boston data set has been deleted. That was considered to have had some improper bias to it, and is considered a bad data model. It was unethically collected, as it turns out, in the original place, which is kind of weird for a housing data set. But anyhow, so you can reference this and read through it on your own time. I'm not going to take up more time in the lecture here with this, but we can talk. You can see the difference between ridge and lasso regression in this example here. And there's plenty of other online sources. I just grabbed a simple one for you to look at here. This is, remind myself, yes, ridge regression. And this is kind of where the diagrams came from on ridge versus lasso regression. If you go out here to the summary on these, it's another way to get a good reading time on there. Okay. Any questions at this point about lasso and ridge regression? Okay. We'll get a homework ready for you on that. Now it's 11:30. So I'm going to briefly on the midterm exam, kind of get us planned out where we're going to go on this, let you know what the ideas are, by discussing what we did last semester on the midterm exam. And we'll see if there's any, uprisings today discussing these midterm topics. Let me know if I need to change something around here. All right. Before I go into that, let me go ahead and stop and start recording again.